Today, today our talk is Parametrix technique for Lévy-type model with unbounded coefficients, and the speaker is Victoria Knopova. Please, Victoria.
Thank you very much. It's my pleasure to give a talk at this seminar again. So this is my plan for today. The talk is based on the ongoing work with Lorenzo Marino and Stefano Minozzi. So the work is in progress still, and it's also based on my previous work with Alex Kulik and Rene Schilling. There is a serious paper on this topic, but in this talk I will tell you something new. The first part will be just the general knowledge, because as I know the audience is quite mixed. So the first 8 or 9 slides will be the state of art. Then I said our framework, what is new is that we'll try to handle the case when we have unbounded coefficients. By unbounded, I mean that we have unbounded drift, and we also have unbounded in X Lévy-type term. So I present the result, and I assume the topic is quite technical. I present only the key ideas. I explain in which places in which places we have difficulties and how we overcome these difficulties. And on the last few slides, I put some overview. If I have time, I comment a few other results. So at first, let us consider a Brownian motion. A Brownian motion, as everybody knows here, is a process with independent and stationary increments, and the trajectory is continuous. And if we take the transition probability density, where BS is a starting point, X is a starting point, then the density has this nice representation. And it's easy to check that this object is the fundamental solution of the backward Kolmogorov equation. So this equation, and by the fundamental solution, I mean that if we insert this function, the equation will get 0, but also if S tends to T, this function tends to the delta function. Further, we can define the function u of tx as the expectation of f of bt. I assume that f is good. Then one can check that we have that this function is a solution to the Cauchy problem with initial data f of x. Okay, this is, as I said, the general knowledge. Further, for simplicity, I take s equal to 0. Since P is Markov, then this object which we defined on the previous slide is in fact a semigroup. So we have a semigroup property. And it has also Feller property, which means that this PT maps C infinity to C infinity. C infinity, in my talk, it is the space of continuous functions which vanish at infinity. And we also have strong continuity, which means the continuity in this C infinity rho. Further, if you take this operator, define it first on the test functions, then it extends to the generator of the semigroup. The generator is defined in C infinity, and D of A is the domain of this generator. And also, we have the Martin if we define a process M of t, then this process is a martingale with respect to the natural filtration generated by BT, and this martingale problem is well posed, which means that MT is in fact the unique process which is a martingale with respect to this filtration. So we mean if we have two initial distributions, then they define the same process. By this, we need that the martingale problem is well posed. Okay. Let us go a little bit further. I suppose we take B and sigma good coefficients. By good, I mean that we have Lipschitz property and linear growth, at most linear growth. So sigma and B are Lipschitz and with linear growth. And we consider this is D. Okay, then we have a strong solution, and we have the unique process, and we can define the expectation, we can define this PTF of X, and we can show that the martingale problem for an operator which we construct from these coefficients. So I mean, we take this operator. So the martingale problem for this operator is well posed. So in fact, we want to go one step further from Brownian motion and consider the diffusion process. On the other hand, so on the other hand, we can take this operator L and try to solve this equation and try to show that the solution indeed exists, and the solution has the same property as the density of the Brownian motion, in the sense that it tends to the delta function when S goes to T. And so that this solution is the fundamental solution for this equation. And then we can also show that this operator can be extended to the generator of the semigroup, which is defined by this relation. Now let us go one step further. We can take here not the Brownian motion, but we can take here a Lévy process and try to do the same. Yep. Sorry. This problem is much more complicated as in this diffusion setting, because a Lévy process has jumps. In general, we do not have so nice density as for the Brownian motion. The density has much complicated. It has much more complicated structure. So the problem goes. This problem becomes more complex. Let us consider the right-hand side of this problem. So suppose we want to start not with an SDE, but we want to start with a partial differential equation. In this diffusion setting, if we take L as before, we can try to solve first this partial differential equation, and then try to associate with the solution a Markov process and try to show the uniqueness. In some sense, this is another view of the same problem. If you want to construct a process, we can start with an SDE, solve SDE, prove the Markov property, and then we get a Markov process. But alternatively, we can proceed in analytic way. We can start with a partial differential equation and try to solve this problem. I try to solve this problem analytically. If we are talking about the partial differential equation, this method about which I will talk, it has a long history. It's called the Parametrix method, and it was first proposed by Eugenio Lévy. It's quite old. The framework was purely analytic. He did not think about constructing a process. So the idea was to construct a solution of a partial differential equation in some special way, and then to show that the solution is actually unique. When we construct the solution to this equation, we can proceed in the following way. We can make an educated guess to assume that we can construct the solution in the form of convergent series, and then justify that yes, we indeed have the series and the series are convergent, and then show that the object we constructed is indeed in the domain of this operator. When we take an operator N, at the beginning we assume that this operator is defined on test functions, and the problem when we start in this analytic framework to show that the constructed object is indeed in the domain of the of this operator. It's not necessarily it's not necessarily that we obtain that this pt xy is in this space, but it can happen that this object is in the domain of the extended of the extension of this operator. So, and now I would like to extend this problem to some more general setting. So assume that we start not just with the differential operator, but we start with some integral differential operator defined on some test space. So let us take again the space C to C. C means that we have compact, that these functions have compact support. And try to do the following. One can try to solve this problem by applying a modification of the parametrics method then we get some heuristic representation of the solution. We write it in the form of series. Yeah, I write it. Yeah, okay, I will specify the series a little bit later. So,
Victoria,
yeah.
can I ask you the following question? When we discuss the partial differential equation related to diffusion process or initially to Brownian motion, we get a special form of the differential operator L. So we show that this differential operator is when it is defined on its domain of definition is like non-negative, yeah? Or,
Yeah.
So now you said just take integral differential operator. It can happen that we lost something and we have no hope to get some probability semigroup, yes?
Yes. I will talk about this on the next slide. So in the
Mhm.
next slide, I specify that in order to get a Markov process, the operator must have a very specific structure. Yeah, thank you. I come to this in a few minutes. So I want to formulate the general problem like this. We have some integral differential operator, and we want to construct we want to construct in the end a Markov process. So assume that we can solve this problem. Then if our operator has a special structure, then we get we can show that this object is in fact a transition density of some Markov process. So this structure comes here. I will explain which structure we need. And then if our coefficients in this operator are good enough, we can get the uniqueness. So one way to get the uniqueness is to show that the martingale problem is well posed. But in fact, there is another way. One can show that this object is in the closure of this operator, and this closure is a generator of a Markov semigroup. This is another way. It is also possible, but I will speak about this red way. So the blue way is a way when we have some process, and then in order to get the uniqueness, we want to extend an operator and talk about a generator. Yeah, but with the extension, it's problematic sometimes. And now we come to the question which you posed. So what kind of L we need to take in order to have a Feller generator? And actually, when the martingale problem is well posed. So what is responsible for the Markov property? For the Markov the property which we need for Markov is a positive maximum principle. So if x0 is the argument of a function in the test space, then this L is non-negative at this point. And exactly as you said, in the diffusion case, our operator has this PMP property. And this is a property we will need in order to construct a Markov semigroup. I explain in a moment why. So what kind of operator we need to take? So for what operators do we have this PMP? Consider L in this form. So we have the diffusion part, and we have the jump part. Here I take F from as a test space. This mu is a Lévy-type kernel, which means that it integrates the minimum of u square and 1. B is some drift, and Q is positive semi-definite. Well, if we want to have non-degenerate, we need to have positive definite. And it is a result of Walter-Ho that for these operators we have PMP. Sorry?
Not cohesion subcommittee order.
Excuse me, I didn't get once more, please.
Under which assumptions on coefficients this result of Hoch is valid?
He had bounded coefficients. In principle, that's all.
No smoothness, nothing.
No.
Okay.
No, that's exactly the point. He had just bounded coefficients. In principle, for unbounded, it's also possible. In some cases, we need to have at most linear growth of coefficients. It's a result of Franziska Kuhn. I quote it later.
Okay, thank you.
Yeah. But if you want to get some continuity, we need to assume more. We need to assume that the coefficients are continuous. So under these assumptions, this operator maps CC to as a space of continuous functions. And actually, these are the operators. So these are the only operators which have this PMP property. So it's a famous result of Kuresh that if our operator has a PMP property and this operator and the test functions are in the domain, and then this operator must have this representation. So if you want to arrive at the end at the Markov process, we need to work with operators like that. In my talk, I will assume that we do not have this part because in the parametrics construction, the presence of the diffusion component makes things easier. And in fact, we want to have the jump part, and we want the jump part and the drift. So no diffusion. I want to comment just a little bit about the name Lévy-type. The name Lévy-type comes from the following argumentation. So if we start with an arithmetic Brownian motion, okay, we define a semigroup. This is a representation of the generator of this PT on the test functions. And if you want to go further and we want to consider the diffusion case, so we insert here some coefficients. We insert here some x dependence. So now, if we take a Lévy process, if we start with a Lévy process, if you write a semigroup, then the representation of the generator of good functions has this form, and the correspondence between Lévy and Lévy-type is similar to the correspondence between the arithmetic Brownian motion and diffusion. So in arithmetic Brownian motion, the coefficients are fixed. Here we have x dependence, and here in the representation of the generator for Lévy-type process, we have X dependence in the drift, in the diffusion coefficient, and in the Lévy measure. So this means that in the short time setting, a Lévy process resembles in some way a Lévy-type process resembles in some way a process with independent increments. Of course, in this case, the independence of the corresponding process are not independent, but if you look at trajectories, the trajectories are somehow similar. So that's why we have the name Lévy-type. So, and now I come to the problem, actually. The problem, how to solve the equation of this type for diffusion processes, for diffusion operator, as I said, has a long history. For the integral differential operator, the history is not so old. The first who considered this type of problem was Ferrer in 1936, but he added bounded jumps. And then there was almost nothing for many years, and then there were a series of papers, actually by Kyiv authors, where this operator L had an alpha stable component in the non-local part of the operator. And recently there are many papers on this topic when this operator is a Lévy-type of operator, as I wrote before, but in almost all cases, it was assumed that the coefficients are bounded. So why in almost all? Because there are a few papers where the drift was unbounded, but this kernel was still bounded. So there are papers of Alexei Kulik, and almost at this, a little bit later, the paper of Menotz and Zhang. So they treated unbounded drift but bounded jump kernel. There was also a paper with unbounded drift in parabolic setting, but as I said, I want to talk about the jump cases, not about parabolic cases. So what is so specific for unbounded case? I state first result, and then I explain what are these some conditions. So the result is the following. Under some assumptions on the drift and on the kernel mu, it's possible to show that the martingale problem for the operator L as here, so of this form, but without diffusion. So the martingale problem is well posed, and the solution is a strong Feather process. And in addition, we have a transition probability density. We have a recent paper with Kulik and René Schilling, where we outlined the case still with bounded coefficients, but with a kernel mu, which includes the alpha stable-like case. And in this paper, we outlined the strategy of this proof, a so-called the roadmap. And roughly speaking, this roadmap consists of 3 steps. First, I will write a candidate for the solution to this equation, plus L. So at first we write a candidate for the fundamental solution to this equation. And what is crucial here is if we are looking for the representation of this P in this form, the very crucial step in all this construction is the choice of this 0-order approximation. So the structure of P we are looking for is the convolution of some kernel with some f, which we construct in the proof. I'll show you what it is. And here it is a space-time convolution of this kernel. And this sign, it also means the space-time convolution. So on this step, we have a few crucial points. The first point is how to choose this 0-order approximation and how to show the convergence. And actually, the machinery on this step, which we use to prove the convergence.
So, Victoria, am I right that if you take some other initial P0, then you cannot prove convergence, or series can be with bad properties can disconverge and something?
No.
So what is the meaning of good choice?
We need to start with a good kernel so that we can represent the solution to this equation in this form. So we need to make a wild guess what might be a kernel. Yeah, okay. Okay, I think I just make a jump and explain this at first. No. Wait a sec. I had the slide, but I don't remember which slide it was. Yeah, it was here. So the idea is the following. This is actually the Lévy's method. So the idea is that we are looking for the solution in the form of the main part plus the remainder. The remainder is meant in the integral sense. So if we integrate this equation, then this part in the integral sense is small. So in this sense, it is the remainder. So the question is how to choose the main part and how to choose the remainder in such a way that we can write the solution in the form of the series, and the series are convergent. So I think I explained now how one chooses the zero-order approximation.
You just
Or
explain
how
the
one
problem.
chooses this reminder. Sorry?
You explain the problem, but you don't say how do you do this.
I will present the particular form of this P0.
Okay,
Yeah.
Let's go on.
Okay, then this is 19, and that was, I guess, 12. Yeah. So, a little bit later, I will provide the explicit representation of this P0. So this is not the case that for other P0 we get the divergence. This is the way how we construct the representation of the fundamental solution. We need to construct it in such a way that we have this convergence, otherwise the method is not working. So what is crucial here? The property of this function which we choose, they allow us to transfer this method to these three steps. So if we manage in the case when we have unbounded coefficients, prove necessary estimates for this zero-order approximation, then part 2 and part 3 goes almost automatically. What is important in part 2 is the structure of our operator, so that we have P and P. And in this part, we need some regularity, which we get from here. No, that's the way around. I will tell you today only about this part, because these two, in principle, they come from this paper, but the unbounded case comes here. So, and now the assumptions. These assumptions are quite natural because we want to have unbounded jumps. We want to be non-degenerate. This assumption we hope to remove further. It's just a technical in order not to have too complicated interplay between the drift and the drift which comes from here. But the next assumptions are something crucial. So we take the lower and upper functions. They are called the Pruitt functions because of the Pruitt functions introduced by Pruitt in the 60s for the Lévy case. And now we have Lévy-type. We have here x. Y upper and low because we have, in fact, CL smaller than constant, smaller than Psi upper without constant, sharp. And we also need this function Psi star. The next assumption is the assumption how much our function oscillates in Xi. So this is the assumption that we can bound our Psi upper by Psi lower. And here is some beta, which in principle is R dependent. So we have different beta for small r and for big R. Now this is again the case which does not appear. Yeah. It's important in this case to have both small time and large time behavior, because this is special for the case of unbounded coefficient. From this assumption, after some technique, one can derive that in fact this psi star function has power growth near zero and at infinity. And now we pose some assumption on this function. So we assume that this function must have sublinear growth, and actually not only sublinear, but this v must be less than the minimum of 1 alpha minimum at infinity and alpha minimum at 0. In principle, one can always take alpha minimum at 0 equal to 2, and one can always take this alpha maximum also equal to 2. But for convenience, we keep them separate. And now this is a crucial assumption which does not appear in the bounded coefficient case, but for unbounded coefficient case, it plays the key role. When we construct the estimates of the kernel P0, which I will show you later, roughly speaking, we need to distinguish two types of points: points which are close and points which are remote. And what do we mean by close points? We mean points y which are in this set, or in this domain. When we are in the bounded coefficients case, we mean
Vika,
that,
excuse me. So
yeah.
If x is large, then y can be far
Large.
from x.
Yeah. Yeah. Yeah, it is apart. It is far from x, but this far we control.
Mm-hmm. Thank you.
And in this domain, we put one more assumption on our function psi star. I show on the next slide on when this assumption is satisfied. In this domain, we assume that we can replace x and y, which means that there exist some functions epsilon such that we can change a little bit the power in R here and here, and these functions are comparable. I think I produce the example now. So take a mu xy in this form. In this case, our psi star xr is just comparable to m of x, and here r alpha of x. It's m. And of course, this condition that psi upper is controlled by psi lower is satisfied. I wrote here universal constant, but in fact, one can write this inequality with a constant which is x dependent, but we need a universal one. And for this alpha, we can do the following. We can take y in this region and estimate alpha of y in the following way. So this v is just, so I took here some v smaller than 1. For this v, we can produce explicitly epsilon 1, it's epsilon 2, I guess. Yeah. And we can produce explicitly epsilon1 and epsilon2 such that we have this assumption on psi star. So we can bound mx to the alpha y, and this is our psi star in yeah, here should be y, sorry. So this is comparable to our psi star in the point y, and this is comparable to our psi star at the point x. So at least in this case, we have this assumption. We need actually one more assumption. This is the assumption on the regularity in x of the kernel and of the regularity. It is the assumption on the regularity of the drift. I wrote it in such a form, so we have some part for small u, some part for big U, but what this assumption implies is that essentially we can differentiate as a function psi upper almost everywhere, and the derivative is bounded from above by cx r, and here 1 plus x. So this 1 plus x in the denominator is crucial for the unbounded case. So by this 1 plus x, we control the growth which we have due to the growth in x in the kernel. And again, for this alpha stabile case, we have this assumption. Yeah, and one more assumption is the assumption on the drift. So we assume that our drift is Hölder continuous. This gamma, sorry, this gamma is related to the minimal growth of our psi star function in R. So this is the minimal growth of this function at infinity. And we need this a so-called balance condition. So if we have these assumptions, then we have the theorem. Now I come to the choice of our zero-order approximation, and I explain in which places we actually need this this condition where we replace x and y. So for the parametrics method, we need to show the convergence of these sets. And important here is how we choose the zero-order approximations, and we also need the estimates of this P0. Why? Because in order to show this convergence, we need to estimate these objects and we need to estimate this object. This must be bounded by a constant, and this must be bounded by T minus S, and here it's -1 plus some epsilon. So the choice of P0 must be such that we have these two things. How we do this? For the zero-order approximation, we take a transition probability density we take an object which resembles a transition probability density of a Lévy process with parameters which are frozen at some point. Which approximation I mean? First of all, assume that we freeze here the Lévy measure at some point y. So we have the equation we differentiate in S, and we apply the operator in X. So when we choose P0, we have one point at which we freeze the parameters, and then we play a little bit with this freezing. So let us cut the Lévy measure on some time-dependent level. Then write an expression which resembles a Lévy exponent, the exponent which stays in. If you write the characteristic function of a Lévy process, we have some expression of type e to the minus t psi, and we take this function psi, but we cut the integral here on some special level, and then we take the inverse Fourier transform to get a density. And so the question is how to choose this cutting level. When we choose this cutting level, we have also one side problem. In the case when we have drift and jumps, and drift is more important than jumps. So when the drift is more important than jumps, we cannot ignore this, because if we ignore the fact that the drift dominates jump, if we take the density of a Lévy process with this dominating drift, and we consider the derivatives, then the derivatives are bad. So we cannot work with the derivative of such an object, because we are not able to prove the convergence of our series, because everything explodes. So we need to incorporate somehow the drift. We assume that our drift is Herder, and that's why we need first we first need to modify this drift a little bit. I mean that we take the drift and we modify it. So we take a Friedrichs modifier and we consider the convolution of our initial drift with this modifier. And then we take a flow. Our flow is governed by this modified drift. The only problem is that it's not quite a flow, because we have here a t component, and we do not have anymore this nice flow property. Nevertheless, the right-hand side and the left-hand side are somehow close. And in this flow, we can replace, if we consider a points as Z and Z prime, which are somehow close, we can switch the flow from here to here. And we have some reminder. So why we need this flow? We need this flow in order to incorporate it in our zero-order approximation. So in fact, we take the flow which comes from the drift, and we insert it in our Lévy measure, and we insert it in our cutting level. And then we consider this kind of Lévy exponent. But now the crucial thing, we need to choose this function f. How do we do this? To choose this function f, we take the generalized inverse of this psi star. Our working example is an alpha stable-like case. So when this psi star is, say, m of x r alpha of x, then this function, this function rho is just 1 over m of x alpha of x, and tau is m of x 1 over alpha x. And here comes the crucial difference between the case of bounded coefficients and unbounded, because in the case of unbounded coefficients, this might explode. And now finally, I write my zero-order approximation. So we take the cutting level, this function, but we insert the time argument, not just r, we insert something which is a little bit bigger than this r. Oops, sorry. We cut, if we take this function psi star, we cut away not a ball of size m of x 1 over alpha x. So we cut away a little bit bigger domain. We cut away this domain. So here is t omega, and here m of x. So this domain is a little bit bigger. But the price of this, that then this object is integrable in R. So if we cut this domain, we can integrate this psi in R, and this is important. Now my zero-order approximation. We take this function as our zero-order approximation. I'm sorry, not this one, but this one. We take this psi tilde, and then we shift here by our flow in order to incorporate the drift, if the drift is important, and then this is our function. This idea comes from our early papers, but the crucial difference in the case when the coefficients are unbounded is that the values of our generalized inverse are also unbounded. And in order to get the necessary properties of P0, we need more. I present now which properties I mean. This P0, it behaves like a fundamental solution to some equation. So this L, this operator L resembles a Lévy operator. So Z here is fixed, and T is also fixed. But we cut the integration domain of this function mu as the time dependent way. And we also add some part which comes from the drift. If we differentiate this P0, we get the solution to this equation. It's not a hard part. The hard part is to show that this function is indeed the fundamental solution. And to show that it is a fundamental solution, we need to know how we integrate this function P0. So we need to know the properties of this P0. And what is important here? Actually, this proposition is the key tool to show all the necessary properties of P0 which we need for our construction. To prove this proposition, we need to do essentially a few things. So we need to cut the integration domain into a few parts. One part is where the points X and Y are somehow close. So as you see, here we have T and Y, and here we have S and X, and we integrate in Y. It's not a problem to integrate this function when we have Y only here. The real problem is to integrate it here. And to show that this P0 is so-called Hölder continuous in this integral sense, we indeed need to know what points are close and what points are far. And here is the key thing we need to show. It's a key. It's a key assumption we need to prove this proposition. And what we have in this domain, when I defined this domain, I didn't specify A and B. So in fact, what domains we consider? We consider something like that. When the distance between a point Y, which is moved by this flow, and X is smaller than this tau Ty. I think I write it just for the alpha stabile case, then it will be clear. So in the alpha stabile case, this estimates look like St of Y. Here we have T minus S, and here we have 1 over alpha X or Y. It's not important because in this domain we can replace X and Y. So in principle, I can put here x and it will be the same function, but maybe we have a different concept. And this is a crucial thing when we needed a sublinear growth in the coefficient of the Lévy-type measure. So in the alpha stabile case, this function than slower than x, and then we appear in the domain of this type, and in the domain of this type, it's not important whether we have here y or we have here x, so we can swap them. In the case when the coefficients are bounded, then this is just a constant, and by close points we mean points which are inside of a ball of some small radius. Here the radius is not small, but nevertheless these points in our setting are close, and it's possible to show this further regularity of the density. And do I have 3 more minutes?
Yes, you have.
Yeah. Okay. So if we have nice P0, by nice I mean that we have these properties, and actually we have this proposition, and we use this proposition to prove that properties, then it's possible to get nice estimates on this object, on our phi. By nice, I mean that we can estimate the supremum by something which is integrable in T. And then this estimate is inherited by the series. So it's possible to derive from this estimate the same estimate for the sum. So what we use here? In fact, the hardest proof was already in that proposition. So in order to estimate phi, we just need to split it in a careful way. So here we have a part which came from the drift. If we are in the case of bounded coefficients, I would say that this is the part when the jumps are small, but in this case it can be large, but nevertheless we can handle it. And this is a remainder, and this is a remainder. And in order to estimate all these terms, we need to use the Lipschitz regularity of this kernel. It was that estimate which I named C upper is less than C star. C star 1 plus x. And here we need to use the properties, the integrability of this function, plus we need to use this nice property. And actually, here one can see why we need an extra exponent here in T in order to have integrability on the right hand side. Otherwise, we have T minus 1, and this is not integrable. So to conclude, if we want to handle the case of unbounded coefficients, we need to take the upper to take the Lévy-type measure such that if we if in this Lévy-type measure, if in this Lévy-type measure the point x doesn't run too fast to infinity, or if it runs to yeah, okay, x u here du u alpha x plus d. So if these coefficients are not bad, so that in some regions we can a little bit move here, a little bit move here, then we still can handle the parametrics method for the unbounded setting. So this is the message. I think that's already all. And here is some history, and I promised to say a few words about the existence of martingale problem with unbounded coefficients. In this, there are two recent papers of Franziska Kyiv where she has shown that if the coefficients are unbounded, but unbounded in a sublinear way, then one still can have a solution to the martingale problem, but the uniqueness may fail. And she gave some examples when uniqueness fails. So that's all what I wanted to say. Thank you.
Thank you very much for interesting talk with so many details. And maybe somebody have questions or comments, please.
Maybe I have a question.
Okay, Yana, please go.
So the corresponding processes, they are just Markov or some a little bit better, or you cannot say like it's harmed or whatever. Of course, not failure necessarily, but at least.
Markov failure. So we have the failure property.
So you have failure process still.
Yeah, I have failure.
So then the question is, what is the difference between failure processes and Lévy-type processes? Is there a difference?
Lévy-type is just a general class of processes. In the Lévy-type case, you can have even non-Markov. This is exactly what Franziska Kyiv has shown when she constructed. She took an operator with PMP L.
Okay.
But
so we start with this integral differential operator from the
yes, so we get Lévy-type, but we don't get uniqueness.
Yes.
And since I don't know at the moment what to do if we don't have uniqueness, I wanted to have uniqueness and to have other, because the aim why we wanted to treat the unbounded coefficient cases, because we wanted to study ergodic properties, and we wanted to have a unique process. We did not want to have something.
Okay, so in your approach, you get failure again. Failure process.
Yeah.
But in principle, one may hope to get, starting from this integral differential operator as generator, one can get just a Markov, not even...
Or even non-Markov.
Or even non-Markov.
Yeah.
Cool. No, even non-Markov, it's well...
No. I mean that it has a Markov extension, which is...
Okay, so almost Markov anyway.
Yeah.
Okay.
I mean non-unique. Yeah.
Okay.
Okay, and do you have uniqueness in some class? Like Holder,
You mean the uniqueness of the solution to this problem, right? Right?
mhm.
We did something like that in the case of bounded coefficients, but it is a very complicated problem to show in which class is this operator. Because, yeah, in the case of bounded coefficients, we had this in the paper with Krzysztof Bogdan and Paweł Sztonek. So we constructed the extension of the domain of this L and show that this P is in the extension of this domain. But the approach with martingale problem is more elegant. So if we are not interested in some particular regularity property of P, then for our needs it's enough to have the uniqueness of martingale problem, and that's it.
And can you prove that your process satisfies some stochastic differential equation?
I think yes. I think yes, because okay. I don't know. I don't. Yeah. Okay. Let me put it like that. What I know that if we start with variable jump size, so if you write our L, yeah, skip the drift. If I write my L as what you okay, k xu minus f of x minus k xu u, and here the indicator. I guess no, here is no u, and here is no u. I guess if you take your operator in this form, and mu is a Lévy measure, which corresponds to some Lévy process, then you will have something like that. K x s minus.
From integral.
Yeah. Integral. S and
Compensated measure, maybe.
yeah.
S is U, compensated measure.
And plus, yeah, I will. Again, K. S and here M. So, yeah, but I don't know a straightforward approach how you can. Yeah, okay. You can write your Lévy-type kernel if you make this how does it called shift measure. If you shift
image measure.
Yeah. But okay, you can write an SDE in this form in principle. But then you have variable jump size. If you want to have a variable jump intensity, you need to have an explicit transformation from one representation to another representation, and in the case of stable like, actually I don't know how to write it. So probably it's doable, but I have not seen it like that. And
could you please recall properties of these kernels, mu, x, dy? So I remember you show us that they cannot grow. You have some bounds from above, from below, but are they smooth in some sense in x?
Yeah.
So what was the assumption?
Yeah, this is the growth, this is the regularity, this one.
And where
So,
is
here is x, here is y.
Okay, I see.
Here is x, here is y. I think one can write it for further, but it took us already a big effort to understand which kind of assumption we need in order not to explode, that at the moment I'm happy with Lipschitz.
Thank you. So in some sense, this is some Lipschitz condition.
Yes, it is a Lipschitz condition. So if you are differentiable, your condition would look like this. So you differentiate the upper function in x, and you have a nice bound on your derivative. But it's easier to work with mu than to work with this object. It's more compact, but if you are not alpha stable like, then you have a problem how to write it more or less precisely.
And Q1 and Q2, what are they? Just arbitrary bounded measurable?
Yeah.
So measure mu is such that for arbitrary bounded measurable functions Q1 and Q2, you have the following Lipschitz type condition. I see.
Yeah, we just in one place we needed this condition for big U. In one place we needed it for small U. That's why we wrote it like that. Probably we will improve it because it's not. It doesn't look nice. As I said, we are still in progress.
I have a question. What happens to this method if we add a diffusion part, assuming that coefficients of the diffusion part are smooth and bounded?
If I have diffusion part, it's infinitely easier to guess what the zero order approximation might be. It is
because it seems to me very naively that the main problem is how you deal with this measure and how you make it integrable. So why does adding diffusion makes it easier?
Because if we add the diffusion, your diffusion, we can take as a zero order approximation the density of the diffusion process where the coefficients are frozen in y. And because this is a density of the diffusion process, you have very nice integrability properties.
So we wouldn't need all this machinery for working with measures. We would just need, we will take the part with measure and integrate with respect to Gaussian,
yes. I have
Gaussian estimates.
Yeah, probably yes. I don't remember the papers about diffusion plus unbounded coefficients in measure, but if they are bounded, there are papers, and they just take the diffusion kernel as zero order approximation. They convolve everything, and this diffusion kernel eats everything up. So it really eats all bad things which come from the measure.
I see. Thank you.
So that's why I did not take it, because I wanted the case to be bad.
Okay. Some other questions, please? If there are no, I also have a comment and question that for me, the story began maybe more than 20 years ago in Osaka University, when Takashi Komatsu proposed to me to be a referee of thesis of his student at those time, Asushi Takeuchi, about exactly the behavior of the solution to stochastic differential equation with Poissonian part with such a point measure, compensated and non-compensated. And I remember those talk was very large, like 2 hours continuously.
Yeah.
And after this, when a colleague prepared his doctor's thesis, I asked him about the analog of hyperellipticity Hermander condition for such kind of equation with Lévy measures. And he was able to do this. It was discovered that we need to change time and space simultaneously to do some Malliavin differentiation. And from this point of view, it is very natural to see this theta, which serves as a time change and space simultaneously in the estimation. But let me ask you, do you have something, some conclusions about properties of the solution? Because I think that still those methods can be applied and you can get more information about smoothness of the solution.
I think it can be done because we have some results for the case of bounded coefficients. For unbounded, we don't have them yet, but it is a good, it is a good question. I'm not sure that you will have smoothness if you assume just further continuity of your measure of your measure in X. But I think if you assume Lipschitz, then I'm almost sure that you will have the Lipschitz continuity of your density.
Okay. Okay, then thank you again. And this is finish of our job for today. Maybe Georgi knows the name of the next speaker. Georgi, who will be the next speaker?
It will be Naufel Salhi.
Oh, okay. So let's see you next week. For today, that's all. Bye.
Bye-bye. Thank you.